We're going to find a Vs in the network. And Vs is the voltage over here, and we already know the current going through this branch is over there, and there's another dependent current source, and this current source depends on Vx. If we know this Vx, we'll be able to know this current over there. So this Vx introduces another new variable.
Professor, I have a quick question.
Go ahead.
The K in the denominator for the dependent source, is that 1,000? Does that denote 1,000?
Yes.
Oh, okay. So it's 1,000 units.
So that is something I want to talk about the units. For this problem, you're going to use the unit system of milliamp and volts and a kilo ohm. Milliamp times kilo ohm, that is equal to volts. So this is unit system that works. You don't need kilo ohm, and you don't need to worry about that K. So the reason that you divided by K over there is just to tell you that if you want to use a standard unit, this is how you convert it to standard unit. If we use a unit of milliamp, so over here that is 2Vx milliamp. And Vs is simply the voltage between these two nodes. And if we look at this branch, we know the total voltage that is Vs, and we'll be able to find Vx by using the voltage division. Vx that is equal to the resistor 1K over the total resistance in this branch, that is 2K. So 1 over, you can, if you want to write it clearly, say 1 plus 1 times Vs. So we know that Vx is half Vs. At the same time, I will be able to find the current in these two branches. If I know all the current in all these different branches, I will be able to write a KCL about a certain node. I already find one relationship, and the second relationship will come from KCL or KVL, right? So over here we notice that it's easier to find the current, so I'm going to use all these voltages given or something I'm going to find out to find a KCL equation. So I'm going to say apply KCL to this node A, apply KCL to node A. Now we write the equation. If we count the current leaving the node as a positive, so in this branch that is 2 times Vx, we said the current leaving the node as a positive, so this is a 2Vx milliamp. I use this unit set. So that's a 2Vx, I don't need to worry about the units, and the units are selected from here. And the second branch, the current leaving, that is 2 milliamp. And over here, the current in this branch, if we use the voltage Vs to calculate the current in this branch, we know the current is, if we use that, I will define the reference current goes into VA like that. And similarly, another current will be like that. So the current, let's say this is my current I1 over here. The current I1 is equal to Vs divided by 1. And the current in the second branch over here, the current in the second branch, you can use Vx divided by 1. So that is minus, sorry, because it's a leaving, right? You count the current leaving as a positive. This one goes in, so this is why it's a negative. So we can let it equal to 0. So this is how we find the two equations. And now you have two unknowns, you'll be able to solve the problem, right? Replace Vx by 0.5 Vs, and we simplify the second equation. The first term, 2Vx, that will be 1 Vs, it's a plus 2. And the second one is a minus Vs, so minus Vs, that is gone. And a minus Vx over 1 Vx, that is 0.5 Vs. So minus 0.5 Vs, that is equal to 0. So this is how we find a Vs. So Vs that is equal to 4 volts. Any question for 2.51? Alright, no questions, so we move on to the next problem. So look at this problem. We're going to find I/O in the network. I/O is over here. For a problem with dependent power sources, in addition to the regular KCL or KVL equation, we need to find an additional equation. The additional equation comes from the dependent variable. So it's a Vx. We're going to find a relationship between Vx and some other unknowns in the problem. So by looking at this network, this node connected to almost all these branches, right? And the same thing over here, the node connected to all the branches. I can consider to write a KCL that I will be able to find a relation between the currents. So that is the first equation that I can have. Apply KCL to node A. If we use the current goes into a node as a positive, so we have IO, that is a positive, right? And the current in this branch, which is we can find it from by using Ohm's law, which is Vx divided by 4, right? Plus Vx divided by 4. And the current in this branch that is leaving, so is minus 5. And the current in this branch goes in, that is a plus 3 Vx. So this is how we find the first equation. The second equation comes from a dependent variable, right? This current source depends on another variable, which is Vx. And we need to find a relation between Vx and something else in the problem. Between Vx and IO, Vx is defined something in this branch, and IO is defined in that branch. But these two branches are in parallel, so it means that the voltage on these two branches are the same. So the voltage on the first branch, which is the IO times 6, the voltage on this branch, the total voltage, we can find it as, this will be 2Vx plus 1Vx, so that is in total 3Vx. So that is how we find the relationship between IO and Vx. From the two branches in parallel, we can find the relationship between Vx and IO. Because the two branches are in parallel, we know that the voltage are the same. The voltage of the first branch is a 6IO. The voltage drop on this branch, calculate the current, which is Vx divided by 4. This is the current times the total resistance, which is 8 plus 4. So this is how you find the second equation. After you've done that, you will be able to find IO. You have two equations, you have two unknowns. So combining the two, we'll be able to find IO. So what you can do is that probably find a Vx from the second equation, then plug it back to the first equation. We have a 3Vx that is equal to 6IO, so Vx is equal to 2IO. So we have a 0.5 IO, so this is 6IO, the 7IO plus 0.5 IO, so that is in total 7.5 IO minus 5 is equal to 0. That is equal to 5. So this is how we can find IO. IO that is equal to 2 over 3, right?
0.66.
Yeah. So the unit that is amp. All right. So let's look at the examples that I prepared you for today. So this is the first question. I want to find like one student from your group to help me to define all the nodes by following the method that we taught from last week. I want to see like where it'll solve you, like how you master that content. So I'm gonna need a volunteer from your group to basically like work on this and tell me like to label the nodes, like what we discussed from last week. So anyone who want to volunteer to give a try?
I'll give it a try, Professor.
Okay, good. So you can use the notation function on Zoom to do that.
I don't know how to do that.
So on your,
It's at the top.
Yeah, on the
where
top.
The view
screen.
options panel, you can see the annotate there.
Oh, got it. Thank you. This is it. Let me do that again. Professor, just before I proceed, I'm gonna attack this problem going from right to left because that's the way I think it's supposed to be done. Okay.
You think the three are in series?
Yes.
Look here. This node is connected to something else. These two, at least, they are probably not in series, right?
All right. So it would just be the. I was thinking. Alright. I can combine these two and then add them to the succeeding parallel resistors.
Look at these two resistors. What's wrong with these two resistors? They are connected with a wire. So these two resistors actually is useless in the circuit because you come up from one node, you have like one resistor over there, then you add another resistor over there, then come back to the same node.
I think you have to start from the beginning that two parallel resistors are 1 and 1.
So you think from here, then how about like this,
Yes.
the rest, how they are connected to this? Can you see the series and a parallel relationship right away?
For some of them you can. For some of them you can't.
So,
For instance, the one-to-one resistors, those are technically parallel. And the moment you combine them to make a new resistor, you could take those two, and it's in series with the 2K ohm resistor. So I mean, there are some that you could see, and I believe there are some you can't. You just have
Yeah,
to.
and then you will have triangle and you can go one by one and solve the whole thing.
yeah. So from last week we learned the general method, like how you do it, that's introduced from the textbook. And on top of that, I said, like, let me introduce a method that's not taught in textbook. And you label the nodes and draw the equivalent circuit, right? Do you still remember anyone who want to try using that method?
It's a lot of transformations, like equivalent circuit transformations, right? I mean, I did 1, 2, 3, 4, 5, almost 6 transformations. Is that like too many steps?
Yeah, that is a little bit, that's too many steps. Did you get the final answer already?
I got RT is a 5.46 kilo ohms.
Okay.
But like I said, I did multiple.
So you simplified it as slowly, like by portions that you can see the connection, then put it back in there, then simplify it more. Is that how you did it?
Yeah, I know that seems like a lot of steps, but I just wanted to learn it the right way and then start seeing relationships.
Mm-hmm. Anyone who, so as I mentioned, we learn methods that I said is not taught in the textbook, but I introduced that method by finding the equivalent circuit in one step, right? Do you, anyone
current-
want? Yeah,
Current division?
you want to give a try?
What about current division, Professor?
What about what?
Current division. Oh wait, this is resistors. I'm sorry, never mind.
Yeah, there is no current. We are not looking for a current, right? Starting from the problem, I'm not sure about the connection, but I'm not going to try to understand the full connection right away either. So let's start with the definition of A and a B. Eventually, I want to find the connection between them. Are there any direct connections between them? No. I have to go through something else. Let's define this new node as C. No matter what, it has to go through this node C before you can link to B. And between C and B, are there any direct branches you can identify? Between C and B, let me mark all the B's first. This is my B. This is node B, and this is node B as well. And this is node B, and this is also node B. Are there any direct branches between C and B? Looks like not. I cannot find any branch go through one resistor that will reach B. I cannot find anything like that. So this is why I'm going to define other nodes, say D. Oh, this is also my C. I haven't finished the level in C yet. So this is my C. Are there any direct branches between C and B? Yeah, there is one here. Look. This is C, this is B, right? So I can draw my equivalent network now. So I'm gonna start from node A over there. I have to get to node C before I can do anything else, right? So I first put C over here. So this is my node C. So this is my node A, right? So I start from node A. I'm eventually going to find the connection between node A and B. So let's assume that B is over there. I have to go through the node C before I can do anything else. Between A goes through this 4K resistor. So let me put this 4K over here. Let me put 4. Between C and B, I have one branch which is a 12K over there. At the same time, I have another branch over here that is also pretty straightforward. Between C and B, I can see that directly, so that I will put that down as well. So I'm going to put that down. We have 2K, and at the same time, I have another 2 branches in parallel. So this is my network. Let's put the numbers down there. Put the number down there. So this is my 2K, and we have 1K there. So both of 2 are 1K, so I'm gonna just leave it like that. At the same time, between C and B, there is a one direct branch. So let's mark down what we have already drawn. We did this, we did this resistor, and we're gonna do this resistor. That is 12K. So I draw this resistor 12K over here. Between C and B, I have one branch which is 12K. So now between C and B, there are no longer direct connections. I need to keep looking at other nodes. So let's say if I define this node as D, because this is a new node, it's not connected to anything else, I'm gonna call this node D. And if I define that as a node D, so I will have like multiple Ds. This is a D, and this is a D. This is also D. So I define a new node D in the middle. Then I need to find a connection between C and D, then D to B. Between C and D, how many branches do we have? We have one branch here between C and D, another branch here. Where else we have C and D? C and D, that's it. Oh, C and D here on top, right? Here. We have 2 branches, both are 12. They are connection between C and D. They are both 12K. And between D and B, we want to find the connection between D and B as well. D and B, we have one branch over there. This is between D and B. And this is also between D and B. And this is also between D and B over here, look. We have 3 branches between D and B. And they are all 12. So now we find everything goes through the node C, then D, then to B. Let's see what other nodes that we haven't defined. Oh, this is a new node that we haven't touched yet. So we're going to call that a new node E. So we said we have to go through C. Between C and E, how many branches? C and E, there is 12K. C and E, 12K. And anything else? C and E. No more. Between C and E, we have 2 branches. They are both 12. So this will be my node E. And between E and B, how many branches? So we already did a C and E. This is a 1, and the second one over here. Between E and B, we have a 1, 2, 3. We have all these 3 branches. They are in parallel. They are 12K. 1, this second one, this is third one. That is between my E and B. So we look through all the passes. The only thing that we haven't checked is between D and E. So let's look at if there are any branches between D and E. D is over here, not connected to E, and D is not connected to E, and D is not connected to E. So that is our equivalent network. We touched all the branches, and this 12 and 12, they are connected between D and D. It doesn't do anything. Then we can start to simplify the network. By looking at the problem like this, I believe everyone can simplify the network to find the equivalent resistance. So let's do it block by block. I'm going to simplify this portion first. We call it a resistance R1. So we can find R1 that is equal to 12 in parallel with 12 plus. This is 3 12 in parallel, right? 12 in parallel with 12 in parallel with 12.
So Professor, you're obviously just simplifying it.
Yeah.
Right?
Yeah, so for the rest, I'm going to simplify this. This 12 in parallel with the 12, that is 6. And this is 6 in 12 with 12 in parallel with 12, that is 4. So 4 plus 6, that is 10. 10, we got a 10 kilo ohm. And similarly, we can find the resistance for the second block, which is the same as the first block, is over there. Let's call it a block 2. So we know that block 2 is the same as block 1, right? So that is also equal to 10. So we have a 10, 10, 12, and this one is a 2 plus 0.5, that is a 2.5. So we can simplify the network a little bit more to find the total resistance.
Professor, so we don't need the resistors between D and D?
D and D, that is shorted because it's connected to one node. Then we can find the total resistance for the network. So that is a 4 in series with the rest, right? 4 plus something else. And this will be this branch is a 2 plus 0.5. That is a 2.5 in parallel with 12. Then in parallel with 10. In parallel with 10. So that is our final answer. So what I get is a 224 over 41. And I check the answer. So the unit, that is a kilo ohm.